Okay, hello everyone. So now let's get started. So it's my pleasure to introduce today's colloquium speaker, Professor Dominika Wylezalek. And Dominika got her PhD from the University of Munich and ESO in Garching. And before she joined the faculty at University of Heidelberg, Dominika was an Akbari Mark and Provost Diversity Postdoc Fellow at Johns Hopkins University and also ESO Fellow at ESO in Garching. So Dominika is a world-renowned expert in galaxy clusters, galaxy evolution, and quasar feedback. And furthermore, she's the PI of JWST Early Release Science Program, which I think is one of the most competitive and but also one of the most exciting proposals on Earth. And impressively, all these proposal things happen like 5 years before JWST data arrives. So that's very, very impressive. But all the weight, it totally worth all the wait because as we know, JWST has been a huge success this year and we have seen a lot of your media coverage about your press release. So congratulations. So, okay, today Dominika is going to tell us about multi-phase and multi-scale AGN feedback processes. So let's welcome Dominika, and Dominika, please take it away.
To revolutionize extragalactic astrophysics. What you're seeing here on this image is the first JWST deep field. This is the sharpest and deepest image of the early universe ever taken in the infrared so far. Since JWST has started to take data, many papers have been appearing on the archive reporting revolutionary results, such as the detection of ultra-high redshift galaxy candidates. What's most striking to me when I look at this image is that this image would probably look very different if supermassive black holes didn't take an active part in galaxy evolution and shaping many of the galaxies that we see in this image. This is what motivates my work, and this is also what my talk will be about today, about multi-phase and multi-scale AGN feedback processes. I would like to thank the organizers for inviting me to come to beautiful Princeton. I arrived last night. I'm a bit jet-lagged, but it's beautiful here, and I'm really looking forward to the next few days. I also just realized last week that it's actually Thanksgiving week. It's not something we celebrate at all in Europe. So some of you, or many of you, may already be in a holiday vacation mode. So we'll try to keep this talk entertaining and interesting, and I hope that after that you can go back to finding your best turkey recipe. Most of the work that I will be presenting is work that we are conducting in our fairly newly established research group at the University of Heidelberg. The group is called GALENA, which is short for Galaxy Evolution and AGN. And we are a growing group of early career scientists, basically across all career stages, and all of the group members that are working in our group are doing an extremely good job at plowing through the different difficult data sets that we have. And some of this work you will be seeing in this talk. We're actually also hiring a new postdoc this year. So if you or anyone you know may be interested in a position like this, please feel free to reach out to me. So I want to start my talk with giving you a little bit of background, just covering the basics so we're all on the same page. Coming back to this image, I want to remind you that probably all massive galaxies in the universe, all galaxies that you see in this image, host a supermassive black hole in the center. Sometimes these supermassive black holes go through active phases during which they actively accrete matter, and this is when we call these objects active galactic nuclei, or AGN. And I want to remind you, AGN are events and not objects, meaning that the AGN phase is really just a phase in the evolution of a galaxy. But this phase can have profound effects on the evolution of the host galaxy, and this is because the energy that gets released by the black hole during its accretion, when it accretes matter, can be much, much larger than the binding energy of the host galaxy itself. So from scaling relations, we know that the masses of black holes are about 1,000 times smaller than the masses of the host galaxies. And when we plug in the numbers and calculate what the ratio of these two energies is, we found out that the ratio of the two energies is a factor or much, much larger than 1. Meaning, if just a tiny fraction of that energy that gets released by the black hole can somehow couple to the gas inside the galaxy, that, for example, through launching winds and outflows, that can have a profound effect on the galaxy evolution. And this is kind of crazy when you think about the sizes that are involved, right? Because the supermassive black hole in size compared to the size of the host galaxy is as if you would compare the size of a penny to the size of the moon. So it's a factor of several smaller, but still it can probably shape the evolution of the host galaxies quite a bit. So the term AGN feedback that I will be using quite a bit in my talk really summarizes all the kinetic and radiative output processes from supermassive black holes that affect the host galaxies. This plot now shows you that the topic of AGN feedback is a hot topic, as the slide says. You can here see the number of papers that have been published as a function of time and that have the terms active galactic nuclei or outflows in their abstract or in their title. And you can see that especially in the last 20-25 years, the number of papers has really increased quite a bit. Well, not increased, but really skyrocketed. And this is because people have realized that AGN are an important factor in galaxy evolution. Some of the first observations that led to the idea that AGN and the host galaxies must somehow self-regulate themselves were when it was basically found out that the masses of black holes tightly correlate with the masses of their galaxy bulges. So this is the well-known M-sigma relation that many of you probably have heard of already. But also it has been shown that, for example, galaxy luminosity functions cannot be reproduced in simulations if you don't invoke AGN feedback, if you don't add this additional heating source, energy source into your simulations. If you don't, then you produce way too many massive galaxies at this high mass end of the galaxy luminosity function, producing way too many stars and basically cooling gas way too quickly. There is also ample evidence in simulations that a universe without AGN feedback just doesn't seem to work out. This is a slide that Thiago Costa put together in his review talk for a conference a couple of weeks ago that I took from his review talk, because I think it summarizes quite nicely like how it all goes wrong in simulations if you don't invoke AGN feedback, right? You don't produce galaxy morphology and colors. Galaxies are way too blue, way too disky. You get way too high star formation efficiencies if you don't invoke AGN feedback. You don't quench galaxies, and it goes on and on and on with other parameters also that you don't reproduce if you don't include AGN feedback in your simulations. Okay, so I think these few slides have established feedback is important. We're talking about AGN, but how do we go about and figure out how AGN feedback works and how do we actually observe it? So when you talk to an AGN person, you may be confronted with terms and acronyms like hot dogs, BALs, non-BALs, CFERTs, type 1s, type 2s, liners. So you're confronted with this whole zoo of AGN terms, which may be quite confusing. But I can tell that most of these terms are there because astronomy is a science with a lot of history, and often people, especially back in the days, they observed the sky in one specific wavelength with one specific technique. They found, oh, something is weird is going on in this object, let's call it that way. So many of these terms actually originated from the fact that some objects show specific parameters or quantities in a specific way. But the reason why we have a zoo of AGN terms is because not all AGN are the same. and AGN are sources of both particles and photons. And sometimes AGN have high accretion rate, they accrete at very high rates, they have a high radiative output, sometimes they don't. Sometimes we see that AGN are producing these giant radio jets, these plasma jets, right, that you probably all have seen pictures of, and sometimes they don't. And so AGN can populate this whole parameter space in this jet power versus radiative power parameter. In the extreme cases, you get sources like radio galaxies where you see these giant radio lobes, but when you look in the center, you do actually observe the host galaxy in the optical. Like you don't see much signatures of an AGN if you look at the very center. But then you have these other extreme cases, quasar-like sources that have high radiative output that if you look in the optical, they're completely overshining their host galaxies, but not all of them have radio jets. And then of course, AGN can populate also the parameter space in between. So you get different types of AGN that emit in different wavelength bands that show different signatures in their spectral energy distributions or in their spectra. And this is how these different AGN terms originate. And we also have to be aware that when we look at AGN feedback processes, that AGN are different. In fact, interestingly, there are also two different flavors, two different feedback modes that we associate with these two extreme ends of this distribution. So on the one hand, we have AGN where we see these powerful radio jets plowing into the ISM, heating the atmosphere, but other than that, not doing much else to the host galaxies. In the other extreme cases, and this is more for like these powerful quasars, where we don't necessarily always see radio jets, we see that the AGN is actually capable of launching winds, galaxy-wide winds, that expand into the host galaxy, that sometimes may even be able to remove gas from their host galaxies. So this one mode is often referred to as radio mode, kinetic mode, or maintenance mode feedback, and the other mode as quasar mode, wind mode, and radiative mode feedback. But again, we have this parameter space in between, and there are sources observed where it's not clear which mode dominates or whether maybe both are acting in a way. So please remember that when we talk about feedback and when you read about feedback processes in the literature as well. So to summarize this first part of the introduction, we know AGN feedback is important from simulations. We will see that we have evidence in observations as well that it's a thing, that we observe it, but there are still a lot of open questions, many of them which may seem quite trivial, that we have in this field. Questions regard, for example, AGN outflow sizes and geometries. How big is an outflow? Like, what does the size depend on? How is it impacting its host galaxy? Is it suppressing star formation? Is it enhancing star formation locally and globally? And we know that AGN feedback, AGN outflows are a multi-phase phenomenon. How are these different gas phases connected? And globally or long-term, do we observe an injective or a preventive feedback? So thinking about the methods, I'm an observer. How do we observe feedback processes in general? And there are a couple of methods that are kind of well established, and there are some newer methods that I will not be talking about today. The well-established methods include looking at the emission absorption lines of different gas phases of the ionized gas, the cold neutral gas, the molecular gas phase, just by looking at the geometry of your outflow or of the hot medium in galaxies, but you can also just look at radio emission that may be a byproduct of winds plowing through their host galaxies. And then newer methods include, for example, trying to observe the hot volume filling component of feedback through the SC effect, the Zunyaev-Zeldovich effect, or looking for direct signatures of shock clouds. But again, in this talk, I will be mostly focusing on the methods described above. So one phase that is often looked at when looking for feedback processes is the warm ionized gas phase. And this is because there is an emission line, the O3 line at 5,007 angstrom, that is bright and in the optical that you can observe quite well, at least for low and intermediate redshift objects from the ground. It is a forbidden line and therefore traces low density warm gas on galaxy-wide scale. So it's a very useful tracer for looking at what the AGN does to the ionized gas phase. And the typical signatures that we're looking for are blue asymmetric emission line profiles, where this blue broad component is kind of seen as the smoking gun for having found an outflow. And then if you compute the energetics, it is often related to the AGN sitting in the host galaxy of the particular source. If you have IFU data then, so if you have spatially resolved spectroscopic observations, you can carry out these measurements of measuring the width of the line and the shift with respect to the systemic velocity in every single pixel across the field of view, and you can produce maps of the velocity dispersion and of the velocity offset, for example, to really map out the gas motions and the gas kinematics in the sources, which is a very useful and often used method of investigating AGN-driven outflows in galaxies. The other gas phase that is important to look at is the molecular gas phase, which may be the dominant component of the mass outflow rate, and it's an important component because that's the phase out of which stars form. So we want to understand how feedback actually regulates star formation. We need to understand what the molecular gas phase does. So there are some new observations that have been published in like a couple of years ago, where people have seen high velocity molecular gas clumps with outflow velocities of between 6 and 1,000 kilometers per second, blue shifted, so they are flying out of the galaxy at high redshift. So these are high redshift sources. And it's kind of interesting because it's really the first time that these types of observations are becoming available, just because instrumentation is becoming more and more capable of conducting these types of observations. And the question is here is, are these pre-existing molecular clouds that are being accelerated together with the wind, or is the molecular gas formed in the outflow? And both could be possible, but from these observations, it's not, you cannot really distinguish between the two scenarios just yet. And the question is, what does it mean for star formation if so much molecular gas is removed from the host galaxy? Another method is the direct imaging of radio emission. So as the AGN-driven winds expands and shocks the ISM, you expect some radio emission as a byproduct of that process. And it has been observed potentially in some of the sources. So what you see here is the radio contours are shown in the cyan color. And then in green, you see the high velocity component of the ionized gas, and the morphology matches beautifully, right? So you may expect that the origin of this radio emission is linked to the outflow activity, but because outflows in many cases are bipolar, the morphology of the radio emission is also kind of bipolar. So it may also be small scale radio jets that are actually powering some of the outflows that we see in these sources. And that is one of the big questions that is currently debated in the AGN feedback community, whether it is small scale jets or outflow that are producing radio emission in radio quiet AGN. So you can kind of see that looking at or trying to find out whether what AGN feedback does in galaxies is really not a trivial question to answer. It's a multi-phase, it's a multi-scale question or problem. And also we have the whole cosmic time that is also impacting our work, right? AGN in the low redshift universe are not the same as AGN and more powerful quasars in the high redshift universe. And you may have seen this beautiful picture here that was published in a paper from Tomlinson et al. 2017 that kind of shows the whole baryon cycle that affects the evolution of host galaxy or of a galaxy. And so it's gas flows on many different scales do play a role in different ways. And so does AGN feedback. So I'm trying to divide up my talk into 3 parts. The first part will be focusing on our observations of feedback processes in low redshift AGN, probing scales of like a few kiloparsecs. The second part of the talk will focus on slightly larger scales, going out to tens of kiloparsec in sources at, well, now I have to say with JWST intermediate redshift, 0.5 to 3. And then the last part of my talk will focus on more high redshift galaxies, ultra redshift 5, maybe it's intermediate redshift by now, probing scales of like 7 to 300 kiloparsec. Okay, so let me start with the first part, looking at low redshift targets, probing a few kiloparsec. Here, most of the work is actually using data from the MANGA survey, which is a large IUVU survey that has been carried out as part of SDSS4. All the data is public by now. It has observed 10,000 galaxies with a spatial resolution of about 1.5 to 2 arcseconds. And MANGA is a galaxy survey, but just by pure number statistics, we expect about 1,000 AGN to be among those galaxies. The question is first now, how do we find these AGN? So you can do an optical selection based on well-known line ratio diagnostics using spectra from MANGA. But what MANGA enables us is that we have a whole new axis that we can use, namely the spatial dimension, that we can leverage to better select our AGN. So what we did a couple of years ago is that we developed an IView-based AGN selection algorithm that uses BPT diagnostics, so line ratio diagnostics, across the whole field of view of the MANGA data to select MANGA, to optically select AGN in MANGA. And so what is quite interesting, this galaxy here, the yellow shaded region shows you all the pixels that are consistent with photonization from an AGN. And the white circle shows you the size of the single fiber. So this is where all the spectral information of this galaxy came from prior to MANGA. So we knew something about the galaxy based on this spatial region. And we would have selected it as to be an AGN. But then this galaxy here, for example, we find that it is a likely candidate to host an AGN based on the BPT diagnostics, but based on the single fiber observations, we would not necessarily have selected it as an AGN. So adding this additional parameter, adding this additional parameter space offered by the IView observation actually allows us to make hopefully a more complete selection of AGN. And we understand that this selection may also be contaminated by some sources, what we call fake AGN, so we do try to take these effects into account. So this is to select the AGN, but what we really want to understand is these are low luminosity, low redshift AGN. Do we see any evidence for feedback happening in these sources? So what we have shown here is we have measured the velocity width of the O3 line in all sources, in all spectrals and all sources of these galaxies for the MANGA selected AGN in red compared to the non-AGN. And we do see a clear signature for enhanced velocity dispersion in these manga selected AGN, which are potentially related to AGN-driven outflows in these sources.
Sorry, that is the width of the oxygen 3 line?
Yes.
Yep, okay.
So this result that I just showed you was based on a previous manga release only containing about 3,000 galaxies. And a PhD student in our group, Marco Alban, is now reanalyzing the entire data set, so all the 10,000 galaxies, refitting all the O3 emission lines, trying to account for these broad blue shifted components that the manga pipeline doesn't take into account. And he actually finds similar results. So this is now for all sources in manga, and he measures the W80, so the velocity width of the O3 emission line, as a function of radius in manga selected AGN here in, what is this color? Rose or purple, and compares it to the non-AGN. So even across or out to 2 effective radii, we do see a significant enhancement of the velocity dispersion in these low luminosity, low redshift AGN. He then takes, this plot is based on AGN that were optically selected based on the manga data, but you can select your AGN also in different ways. You can look at which sources in your sample would have been selected as AGN if you applied an infrared selection or radio selection or an X-ray selection. So he actually compares the outflow signatures of the W80 as a function of radius in AGN selected through different methods. And what we find is a stark difference between the signatures between the different deselected AGN samples. So the broad line AGN show the most significant signatures of outflows, and the infrared and X-ray AGN actually even more, and the radio selected AGN show the least signatures for outflows. So as I was telling you before, the way you select your AGN actually impacts what you would derive or deduct about feedback processes in these galaxies. So we need to be very, very careful when we look at samples of AGN, how they were selected and how we actually are biasing our results. As I said, these AGN are low luminosity, low redshift. The kinetic coupling efficiencies are very, very low. So they probably, these winds, even if they are there, they probably don't do much to their host galaxy. But the caveat here is that we're only looking at the ionized gas phase, right? We don't know like what the other gas phases do in these sources, but we know that AGN-driven winds are multiphase phenomena. So this is why we started a large follow-up campaign to observe some of the manga galaxies using a radio telescope, the Arizona Radio Telescope, to conduct a CO follow-up to measure what the molecular gas phase is doing. And we have the first data release of this follow-up campaign is out. So we have spectra for about 200 sources. All the data is public, so you can just go to the paper or the website and download your CO luminosities, molecular gas masses, and also the kinematics of the CO gas that we publish. So here are some of the galaxies in our sample and the corresponding CO spectra. The survey is still ongoing, and luckily it does. We were very worried this summer when a large fire was actually threatening Kitt Peak and coming very close to some of the observatories, some of the telescopes. Luckily, miraculously, all the telescopes survived. Some of the infrastructure was destroyed, so some of the roads and the internet and the cables were destroyed by the fire, and it's currently being restored. But once this is all done, we will actually be getting more data on the survey. So we expect to double the sample size in the next few years. What is kind of interesting and what my postdoc Caroline Bertemis is working on is that with the data that we have, she found something very interesting. So the main advantage of this manga follow-up is that we have molecular gas measurements that go with spatially resolved optical spectra, right? So from the optical spectra, she derived metallicity gradients in galaxies in the AGN in the sample, and measured global depletion timescales. So basically the timescale of how quickly a galaxy would run out of its fuel for star formation. And she finds a very significant positive correlation between those two quantities. And for those of you who have not stared at this plot for a year, let me make this a bit more clearer. So what it means that galaxies convert gas more quickly down here and convert the gas more slowly up here. And it means that up here, galaxies have less metals in the galaxy center compared to the outskirts, whereas down here, galaxies have more metals in the galaxy center compared to the outskirts. So we kind of see a redistribution of metals towards the outskirts in galaxies that are more quenched, or in AGN that are more quenched, that convert their gas more slowly. So we think that we put the idea forward that we may actually be seeing the signatures of a redistribution of metals in these host galaxies through prolonged weak AGN outflows acting in these galaxies.
Sorry, maybe it was clear and I missed it. The 187 galaxies, they're all AGN defined classically, or?
No, they are not all AGN. We have, so Mascot, the CO follow-up program, is a galaxy follow-up program. So again, we have some of these 187 galaxies are AGN, but not all. So we do actually have a control sample of galaxies that are not AGN in which we don't see that correlation.
Okay, got it.
So,
yeah.
So if these AGN are somehow related to mergers, this can also be the redistribution due to this merging process?
We exclude mergers.
Okay.
Yeah. Yeah, because we wanted to make sure that no other effects may bias our relation. So we exclude mergers, yeah. And it's quite easy because you can actually resolve the galaxies. You can look at the images. So that leads me to the first summary, which is kept quite simple, even though people not always think that low redshift, low luminosity AGN are important because they are low luminosity. We find do not underestimate them, right? They can be very, very interesting and good test beds for looking at good resolution at different effects and at studying a large sample of galaxies in a way that we couldn't do for high redshift sources right now. But of course, looking at high redshift is quite important. And this leads me to the second part of my talk, now moving to slightly higher redshift and probing scales of a few tens of kiloparsec. So looking at high redshift or higher redshift is important because we know from the star formation rate, the evolution of the star formation rate density in the universe, this peaked between somewhere between redshift 1 and 3, right? So this is what we call the era of cosmic noon. This is where most of the action in the universe happened. And coincidentally, it's also the era where the quasar space density peaked. So really star formation rate density and quasar space density were at their peak at this time. And it's probably where quasars, where AGN made the strongest impact on galaxy evolution. And in fact, we, a couple of years ago, we looked at quasars, very powerful quasars using the Sloan survey, but this was slightly below redshift of 1, and we looked at how the specific star formation rate in these sources relates to the outflow speed that we detected, measuring again the velocity width of the O3 emission line. And we saw hints of a negative correlation where sources with stronger, faster winds seem to reside in galaxies with lower specific star formation rate. But this was using quite a small sample of galaxies. and also quasars that were powerful for their redshift, but not as powerful as it could get at even higher redshift. So a couple of years ago, my collaborators and we discovered a sample of high redshift quasars that we dubbed extremely red quasars that are found at redshift of about 2. And these sources show really unprecedented kinematics in their ionized gas. So what you're supposed to see here is the O3 emission line doublet and the H beta emission line. But some of these sources are so crazy in their kinematics that the doublet, the O3 doublet, is completely blended together, and it all blends even together with the H beta emission line. And some of these sources show full width of maxima of their O3 emission line of 3,000 to 5,000 kilometers per second. So velocities that have never been seen in narrow lines before. So these are probably sources that are going through an initial blowout phase of feedback that may impact their host galaxies quite a bit in the future. And to show you why these sources, or to convince you more that these sources are quite interesting, is shown, I think, in the following plot, where we show the volumetric luminosity of quasars for differently selected samples, and the velocity width of the 3 emission line. And you can see that compared to other quasar samples at the same volumetric luminosity, these extremely red quasars that are colored in red show much more extreme ionized gas kinematics compared to quasars that are very similar in terms of the volumetric luminosity. We also know that these sources are high in stellar mass, so the host galaxies are quite massive. So we think that these sources may be traces of efficient feedback episodes near the end stage of stellar mass and supermassive black hole growth in massive galaxies in the early universe at cosmic nodes. So they're very, very interesting sources to investigate if we want to understand how feedback acts in some of the most extreme cases. But observing these sources from the ground with the same methods as we do for low redshift sources, like I showed you for the manga galaxies, is very, very difficult. So this is why we started this JWST early release science program, which is called Q3D, that is currently using the NearSpec and MIRI IFUs integral field unit spectrographs to spatially resolve the kinematics of the multiphase wind in quasars at between redshift 0.5 and 3, so very high redshift. We're also developing a software package for PSF analysis and decomposition for JWST IFU data. So our sources will be dominated by the central quasar, right? Will be dominated by PSF effects. So this needs to be decomposed first before we can actually look what's going on in the host galaxies of these sources. And the first data release of our software package Q3D Fit was released just last week. So it's available on GitHub. If it's still a work in progress, but if you have IFU data that is PSF dominated, feel free to download this package and play with it. So we provide Jupyter notebooks, example notebooks that walk you through the analysis, and the different steps should be self-explanatory. And ideally, this package will also be able to be used by anyone who wants to subtract a PSF component from the JWST IFU cube. So it could also be non-extragalactic related. So the sources that we observe within this program are between redshift 0.4 and redshift 3. So we kind of picked 3 poster child sources covering a large range of parameter space in the redshift in their host to quasar ratios, just to test the different modes of JWST and see how it performs in different situations. The x-axis shows you now the wavelength range that JWST covers, so going from slightly below 1 micron out to 30 micron. The blue and pink colored regions show you the filters and gratings that we're using for these sources. And as you can see, we chose a setup such that for each of the sources, we will be able to observe traces for the ionized gas phase, here colored in yellow, the molecular gas phase, star formation rate traces, and shock diagnostics. So with this coverage from 1 to 30 micron, we'll be getting information about the multiphase medium in these galaxies. And then, of course, the line-free regions between the emission lines will also allow us to construct narrowband images, continuum images, to look at the underlying continuum of these sources. So the first data cubes have been arriving in the archive. And the first data, I think, came in sometime in July. It was a Sunday, and I was very excited. I told my husband, please take our 2 kids, go somewhere. I want to be by myself on a Sunday. And they went, and I looked at the data cube and I was like, what is going on? I have no clue. So we had observed the source with the intent to map out the outflow. We knew that this redshift 3 source had a blue shifted outflow component at a speed of like 500, 600 kilometers per second. So this was what I was looking at. And then I was browsing through the cube in my tool that I was using. And I started to see all these extra emission components in the O3 line, right? So here what you could see is the O3 doublet. So this is a beautiful narrow emission of the O3 line. But then if you look in different places of the data cube, you start to see broad blue shifted components here, but then you're starting to see extra components that are redshifted. And if you look here, you start to see an even stronger redshifted component, but also a component that is at systemic velocity. And you move through the cube, and then somehow you start to see that the redshifted component is actually stronger than the systemic component. Then you go to 3 here, and you suddenly see 3 components popping up, and here is a redshifted broad component. And when we first looked at the cube, I think we spent the first 2 weeks just staring at it and trying to figure out what is going on. But then we kind of made sense of it because luckily we have supporting data for this. So we not only have this data cube, but we also have an HST image of the source that tells us something about the stellar continuum of other sources, of the quasar itself, but of other sources as well.
So you said, is this an ERQ, this particular object?
This is an ERQ, yeah. So the scale here is about 30 kiloparsec on each side. So this black box now shows you the field of view of the near-spec data cube, and then this blue underlying image is from HST. So the HST shows you this big blob in the north. We know that this is a foreground star, but then it shows you clumps here, which were there, but we didn't really think much about it before we had the near-spec cube. But as it turns out, if you go to the near-spec cube and look at these positions, then narrow emission line components that are coincident with these clumps actually appear at these positions. So what we have confirmed with this near-spec data cube set is that all these clumps, at least 3, possibly more, are actually related to the quasar. But the velocity offsets with respect to the quasar redshift are 600 to 700 kilometers per second at a distance of just 10 to 15 kiloparsec. And then in HST, we also saw this tidal tail, and we thought, okay, the quasar is potentially merger back then, but now with near spec, we confirm first, that this extended emission is actually real, but also the extended emission is not at the same velocity as the quasar, but it is at the same velocity as these companion galaxies, namely at +6 to 800 kilometers per second, which is a very complicated but interesting situation. So we started to look at the literature, and we found that in merging protoclusters, you can get velocity offsets of galaxy groups even for like small projected distances on the sky. So here, this is from a paper of Kuiper et al. 2011. They run a simulation using the Millennium simulation showing the velocity offset in the X, Y, and Z direction for two protocluster groups that are merging, and they merge at the redshifts that are indicated here in the dashed lines. And you can see that the velocity offsets between the groups can be of order of several hundreds of kilometers per second. And so protocluster mergers can lead to situations that we observe with the JWST. And our system may actually be very similar to other protocluster mergers that have been found at low redshift. For example, the spiderweb galaxy cluster that is at redshift around 2. So coming back to our near-spec data cube, it was featured in a NASA and ESA press release. What we think is, what we found without even looking for it, is the signature of a protocluster information, a protocluster information that is actually two dark matter clumps that are merging with each other. And from the velocity offsets, we think that the dark matter clumps are probably of the order of a few 10 to the 13 solar masses each. And if you project that to redshift 0, then this is very likely to become a very, very massive galaxy cluster by redshift 0. So this is not so much about feedback itself, maybe, but it also shows you the extreme discovery space of JWST, right? We found this and we're really looking for it. And I think that when we start to look at these new data sets, we need to be very open about finding new things that we might not have expected to find. So please take a good look at your data and try to interpret them as best as possible.
Do you actually see the galaxies at those positions?
We do see them in HST for sure. And if we look at the continuum from near spec, so we can make narrowband images from the cube, not looking at the lines, only the continuum, we see continuum also at these positions, yes. And so my colleague is actually now doing a more in-depth analysis looking at the ionization structure in the data cube, looking at line ratios and such. And I mean, if you look closely, if you probably change the stretch, there may be another clump here, which may be related to the quasar itself, but may actually be an additional companion galaxy that is in this field of view.
So if that's protocluster, does that mean this ERQ is not at the center of this protocluster? Because now it's like almost like the very edge of this.
Well, I mean, we're only looking at 25 kiloparsec across, so we have no idea what the larger field is doing just now. So we can't really tell. But from other protoclusters, we know that the most massive galaxy in these protoclusters at high redshift is not necessarily always in the center, so it can be quite offset because these things are, they're not virialized yet, they're still information. So the summary 2 is that red quasars at cosmic noon are sites of vigorous AGN feedback. JWST will resolve the multiphase outflows in such sources for the very first time and will do much more as well. Okay, so in the last 5 minutes of my talk, I want to briefly touch on moving to even higher redshift and probing even larger scales, trying to see if we can find signatures even on CGM scales. And here we're focusing now on another specific sample of AGN, namely high redshift radial out AGN, that similarly to ERQs are very massive galaxies that are found in the early universe. they have been shown to be powerful sine phospholipid scale structures. So oftentimes protoclusters are found around them. And they have been shown to also be ideal laboratories to study the interplay of gas in and outflows. These things have giant radio jets, and to look at different modes of AGN feedback at high redshift. So the new set of instruments that have been appearing on the VLT, but also on KEC, are now allowing to look at the rest frame UV emission from these sources on CGM scales. So for example, looking at Lyman alpha, we do see giant Lyman alpha nebulae spanning across several hundreds of kiloparsecs in some cases around these high redshift AGN. So this is an example from a paper a couple of years ago where you see the quasar, or the AGN is here in the middle, the yellow crosses or show you the positions of the radio jets, and then the Lyman alpha emission is seen on several hundreds of kiloparsec scales. And it has been shown that emission at scales of less than 100 kiloparsecs is consistent with AGN photoionization, and everything else is consistent with shock excitation, probably through accretion from the cosmic web. So these makes these things really interesting objects to look at how the whole feedback loop is acting at high redshift. So we have similar data now for 8 of these sources. This shows you a walk through the data cubes around the Lyman alpha emission line. So you can see these nebula showing up and then going away. And if you look closely, you actually see these nebula flickering. So why is that? This is because wherever you look around these radio cloud AGN, which are obscured sources with the type 2 AGN, you see very weird Lyman alpha profiles. You see signatures of multiple absorption troughs that are completely messing up the Lyman alpha profile. So this is an extreme case. You see a deep trough here. You see 8 troughs in this source. Without correcting for this absorption, you would actually underestimate your flux and your Lyman alpha surface densities by quite a bit. So we're currently doing a correction of these absorption troughs and trying to derive the intrinsic Lyman alpha profiles by modeling as best we can the wings of the Lyman alpha emission and trying to extrapolate in between. And you can see that these absorption troughs, they not only seen in the center of the observations, but they're seen across several tens of kiloparsecs, even out to 100 kiloparsec, right? So here you can see the spectra in different positions of this data cube, and you can see that the spectra look very, very weird in all apertures of this source. But what this enables is you can actually use now the information from the absorption troughs to make conclusions or draw conclusions about what is absorbing, what is the cause for the absorption, and on what scales it is distributed. So in a pilot paper that was led by PhD student Wuji Wang at Heidelberg, he modeled the spectrum of our highest redshift source, a redshift 4.5 source. And now we're focusing only on this first absorption trough that is at 0 velocity. So from the modeling, you can deduct column densities and also even the kinematics of the neutral gas that is absorbing, that is causing the absorption. And you can map out now the column density of the gas that is responsible for the absorption as a function of position. So again, here the green contours show you the positions of the radio jets, and this shows you the column density gradient across, I think this is about 60 kiloparsec across. And you can see a clear velocity gradient of two decks, yeah, from 10 to the 14 going up to 10 to the 16. And we can also derive, and this is now for the gas that is causing this absorption, a velocity gradient, right? You can measure actually how the dip of the trough changes as a function of position, and we do see a clear velocity gradient that is actually spatially aligned with the radio jet axis, which is very, very interesting. And yeah, we do see evidence for this absorption, for the same absorption trough, also in other lines that suggest that this, what we call absorber 1, is metal rich with a solar or maybe even supersolar metallicity. And the picture that we come up with is that what we're probably observing is a gaseous shell that has been ejected some time ago, that is expanding into the CGM, and that has been metal enriched through previous star formation or AGN feedback episodes, that is now interacting with the radio jet and causing this velocity, the velocity gradient that we see. So this shows you that looking at these sources can tell you quite a bit about the enrichment also of the CGM in these high redshift sources through AGN and star forming episodes. But we also want to know what's going on in the center and kind of connect the larger scale signatures to the small scale signatures. So Wuji has a JWST cycle 1 program accepted. I think he's one of 2 student PIs who got time in the cycle 1. And he will be using NearSpec to also map the stellar gas and excitation components in these distant radio galaxies. And we're very excited about this project. So that leads me to the third summary. Spatially resolved kinematics of gas and absorbing structures suggest a complex interplay in the CGM, in the circumgalactic medium. So far, it's still unclear to us what the link between type 2 sources is, such as the radio galaxies are, and type 1, where we don't necessarily see these crazy absorption troughs in their spectra. But we're currently conducting an analysis to try and understand what the differences are. So I will leave you with my summary of summaries and looking forward to questions you may have. Thank you.
Any questions for Dominika?
Red quasars. What is the source of the photoionization of the oxygen 3? You think you're seeing the flow obliquely and that the oxygen 3 has a view of photoionizing source, but then you have very high velocities, so that suggests the true velocity is even larger. Or is it shock excited? Shock ionized?
Yeah, that's a good question. So we have, so far we didn't know because we didn't have the signatures to test this. With JWST, we have that now. So we have a preliminary analysis of this data cube that I was showing to you that shows that it's a mix. So we see along the axis where we see signatures of the outflow that the source of the ionization is probably photoionization from the central engine, from the AGN. But then outside, we see signatures actually of shock excitation. So it's a mix of both, yeah.
Any other questions?
For the protocluster that you showed, like, do you know if the system is gravitationally bound or if it was just like a chance encounter?
No, it's probably not yet gravitationally bound. It's like, well, we don't know. It's like, we only have a small view of it for now. And only the fact that we're seeing so many galaxies in such a small projected area lets us say something about the fact that we may have found a protocluster, especially because the velocity offsets of these galaxies are so large. And it's very difficult to reproduce an observations like this without having a merger of two dark matter halos. So it's something that is still very much information.
I wonder, so you showed us this one spectacular, extremely red quasar object. Do you have data on more at this point, or have you shown us the first and most spectacular one, or do the others show similar kinds of signatures?
Yeah, so this was the one that I showed was the first one that was observed back in July, and like within 6 weeks we tried to put together this paper. which was not easy because a lot of technical details with the pipeline and everything are not working. And we have more cubes by now, but everything really just started to come in the last a week and a half.
Oh, okay.
So we're still trying to digest what we're seeing now.
So for the for the CGM, maybe you explained it, but can you summarize for the CGM? Can you tell the contribution or the components of infall and outflow and recycling, and what is the big picture that you can tell about the CGM?
Yeah, okay. So we're not at the stage just yet, because especially Lyman alpha is a very complicated line. It's a resonant line, so it's affected by many different processes. So saying conclusive things about inflow and outflow is very, very difficult with this line alone. The analysis that I showed you here, which was published a few years ago, they tried to make some assumptions on the luminosity of the AGN and its ionizing ability. And so Lyman alpha is clearly detected on scales of several hundreds of kiloparsec, but probably the AGN cannot be responsible for the ionization at these large distances. It can only be responsible for the ionization out to, say, more or less 100 kiloparsec. So the Lyman alpha emission at larger distances must be caused by something else. And you can also see here, the stretch is a bit difficult, but the morphology of the Lyman alpha emission is very filamentary. You may see this here. Yeah, it's difficult to see in the stretch, but it's very filamentary. And it may, like the luminosities, the surface densities are such that it may be explained by infalling gas that is shock excited as it falls in to the host galaxy. But it's all, I mean, it's very uncertain at this point, yeah.
Okay, we are at an hour, so let's thank the speaker, Dominika, again.